All right, so this week, as I said, we're going to look at 1.5 sections. We'll do section 6.5 over a couple days. Section 7.2, which is the next one we do, we'll look at half of it, probably on Friday. All right, so when we work with trig functions, okay, of acute angles, we're pretty much going to focus on right triangles. Can someone just remind me, what's a right triangle again? What makes it rough?
90-degree angle. Yeah,
it's got a 90-degree angle. Okay. So it's a triangle with a 90-degree angle. Now, the side that's opposite the right angle, it's always the longest side because it's across from the biggest angle, has a special name. And what's the name of the longest side in a right triangle? Yeah, it's the hypotenuse. Okay, so just some couple basic things. Hopefully you guys already know this. The other two sides that aren't the hypotenuse, what are those called? Yep.
The legs.
Yep, the two legs. So here's the same thing I just said, except in a picture form. Now, I labeled this angle in the lower right as an acute angle. Why? Why couldn't that be an obtuse angle? Yeah.
Because it's less than 90.
Why does it have to be less than 90 in a right triangle? Like, why couldn't it be like 95?
Because it only equals 180.
Right, all the angles have to add up to 180. We've already used up 90 here. So between the other two, they each have to add up to 90. Okay? So they have to be acute. All right, so let's take a look at the Pythagorean theorem. I'm not really interested in what it is. I'm sure everybody can most people could spit that out and just say a squared plus b squared equals c squared. Why? Anyone know why? A squared plus b squared equals c squared? Well, first, A and B, and I kind of had it up in the picture that's half off the screen, but A and B refer to the two sides that are the what? The legs, and C? High C refers to the hypotenuse. So the idea of the Pythagorean theorem is if you square a leg, square another leg, and add them up, it equals the hypotenuse squared. But we'll look at why. There's probably dozens, maybe hundreds of ways to show why that's true. I think the easiest way is with a picture. Okay, so what I have there is a square within a square. And the inside square, it's kind of tilted. Now, what I want to do is I want to focus on finding an area. And I want to find the area of something two different ways. And what I want to try to find the area of is that big square. That's what I want to find the area of, the big outer square. I'm going to do it a couple different ways. Any questions on what shape we're going to try to find the area of? All right. Now, before we do it, look at what I've labeled. Okay, I have basically 4 triangles within that big square. And if you lay them out the way I did, it makes a smaller square that's kind of tilted a little bit. A and B are the 2 legs, and they're the legs in each of the 4 triangles. And C is the hypotenuse in each of the 4 triangles. All right, so we're going to find the area of a square. So first thing I need is the formula for the area of a square. Madison, what's the formula for area of a square? Length times width. So area of the square, length times width. All right, so let's, you know what I'll do? I'm going to just put it in a different color so we can kind of reference that one. Okay, and I'm going to call that ace, what can I call it? Well, you know what? I'll go like this. I'll go area of, I'll go like that. It's the area of the green square. So I need the length, and then I need the width. Justin, what's the length of the green square?
A plus B.
Yeah, it's a plus b, or b plus a, it doesn't matter. But the length is a plus b. And how about Gabe, what's the width?
A plus B also, right?
Yeah, it's the same thing. It's a square, so they're going to be the same. So a plus b on the top, a plus b down the side. So let's distribute that out and see what we get for the area of the big square. Kathleen, when I distribute this out, do you remember the, sometimes there's a word or a term that you learn in Algebra 1 to remember the pattern to do it in? Yeah, we want to FOIL it. Again, some people don't, you just remember it as the distributive property twice. But let's FOIL that out and see what we get. Ryan, can you FOIL that for me? Tell me what you get.
Okay. A times B, or AB, I guess, or A plus B, A first, outside, inside. AB, when A times B, do you multiply when you do FOIL? Or?
You multiply, yeah.
Okay, so it'd be AD.
I agree. There's going to be an AB in there. There's going to be a couple of them. But if we want to follow FOIL,
A squared.
A squared.
Close one. AB is the next one.
So you're going to get an AB.
And then inside BA.
Another AB. So how many ABs do you have?
2.
2.
And then a B squared.
And a B squared. So that box that I just put around that expression, that's a formula for the area of the green square. That's one way to do it. Okay, any question on how we got that? Now, let's call this way number 1. Let's do it a second way. Let's find the area of the green square again. Someone think they can give me a different approach to finding the area of that green square? Besides just the way we did it. Rob?
Could you find the area of the triangles in the smaller square inside and then add it all together?
So you could find the area of the 4 triangles. Anything else?
And then find the area of the smaller square inside and add it all together?
Yeah. So let's find the area of the 4 triangles and the smaller square, add them together. And we're going to get a different formula, but let's see what happens. So let's start with the small square. What's the area of the small square? Yep.
Is it C times, wait, never mind.
Yep.
C squared.
C squared. C times C.
So it's C times C.
Plus, how many of those small triangles do we have?
4.
We have 4 of them, and they're all the same. So all we have to do is find the area of one of them, and then times 4. All right. Area of a triangle. Let's put that up here. What's the formula for area of a triangle?
Half base height.
Half base times height. Now, it doesn't matter which triangle you pick. You can pick any of them. They're all the same. So what would be the expression for the area of one of those triangles? Yeah?
AB over 2.
Yeah, you could say AB over 2 or 1/2 AB. Doesn't matter. But you're going to find the area of one of them, times it by 4. That's going to give you all of them. Now, we can simplify that a little bit. What's 4 times 1/2 AB? Yeah.
2AB.
2AB. Plus C squared. Let me put that in there. So there's a different formula for the area of the green box. So we have method 1 and method 2. Gives us 2 different formulas, but gets the same shape. So what does that mean about what's in The box for method 1 and the box for method 2. Yeah,
They equal like the same thing.
they equal each other. Right? If you're finding the area of the same thing two different ways, then what's in box 1 and what's in box 2 is exactly the same. So a squared plus 2ab plus b squared equals c squared plus 2ab. Now, there's something I can do there to simplify it a little bit. Yeah,
Minus 2ab.
there you go. And there's your Pythagorean theorem. Minus 2ab minus 2ab, a squared plus b squared equals c squared. That's why. Well, it's one of probably 100 different reasons why. But that's a pretty simple way to show it. Has anyone ever seen that before? And it doesn't really require anything fancier than algebra 1. Just foiling and combine like terms, and that's it. And a little bit of geometry. Just area of a square and a triangle. All right. So that's why the Pythagorean theorem works. All right, so we're going to look at our 6 trig functions that we've already looked at before. Sine, cosine, tangent, secant, cosecant, cotangent. Except now we're going to use terms like opposite, adjacent, and hypotenuse. So I'll give you the definitions first, and then if you're not sure what those terms mean, I'll explain them. Hypotenuse we've already explained. That's the side across from the 90. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And the 3 other ones I have on the right-hand side, right under that gray square. So the 3 on the right are the reciprocals of the 3 on the left. Does anyone remember the name of the trig function that you get when you flip sine? Yep, cosecant. And it's just the sine flipped. It's a hypotenuse over opposite. Okay, the next one is going to be hypotenuse over adjacent, but I want to see if we remember the name of that. Secant, yep. And the last one is adjacent over opposite, and that's the cotangent. Yeah, very good. All right, so most of those, well actually 4 of them, have the hypotenuse in them. Right? Hypotenuse is the side across from the 90. But opposite and adjacent. Do you know what I mean by those? Like, opposite what, adjacent to what? What am I talking about? Yeah, you think you want to give it a shot?
Yeah.
Sure.
The opposite is opposite the acute angle you're trying to work out in the equation, and the adjacent is the one like next to it.
Yeah, so opposite is the one that's across, adjacent is the one that's right next to it. And the reason I describe these as relative terms is because it's like you're trying to talk about like left and right. If I said which way is left, well, it depends on which way you're facing. So for me, left is the door, right is the window. For you, that's the opposite. So the terms opposite and adjacent can change places depending on your perspective. So if the angle that you're trying to figure out is down here, then that makes opposite the side that's furthest away, adjacent the side that's right next to it. Now, if you're looking at the same triangle, but let's say it's kind of like you're going to face a different way, right? You're going to look at everything from the perspective of the angle at the top. Now opposite and adjacent just switched. That's opposite, that's adjacent. Okay? So it all depends on your perspective. What doesn't change is the hypotenuse. The hypotenuse is always across from the 90. Doesn't matter what angle you're trying to figure out. Okay? Either the top or the one at the bottom. So that's kind of like if I said which way is up. Well, if I face the back wall, or I face the door, or I face the board, doesn't matter. Up is always towards the ceiling. That's the same for all of us. But left and right changes depending on my perspective, the way I'm facing. That's kind of like opposite and adjacent. Okay, so any questions on that? All right. So if we have two right triangles with congruent angles, then they are what we call similar. Doesn't mean they're identical. Doesn't mean the triangles are congruent. But it does mean the triangles are similar if all the angles are the same. Why is that important? Well, what that means is the trig functions that we just went over, sine, cosine, all 6 of them, always have the same value for a given angle. Doesn't matter the size of the triangle. Like if you said to me, what's the sine of 10 degrees? And you draw a really small triangle. Or you blow it up, make it bigger. And you say, what's the sine of 10 degrees in the bigger triangle? Doesn't matter. If the angle is the same, the side, this actual size of the triangle doesn't make a difference. Okay, so let's look at this triangle on the left. That's a 30, 60, 90 right triangle with the proper relationships. The hypotenuse is always double the short leg. And the bottom side is the square root of 3. Let's find the sine of 30. So we just said that sine is opposite. If you want to be specific, it's the length of the side opposite divided by the length of the hypotenuse. So what would the sine of 30 be? Yeah.
1/2.
Yeah, 1/2. Sine of 30 degrees is 1/2. Now, let's take that triangle and double the size of it. It's still a 30, 60, 90 right triangle, but I've made every side twice as big. So let's see if that affects the sine of 30. Using the sides in the other triangle, what's the sine of 30 there?
2 over 2 and 3.
2 over what?
2 and 3.
2 over 2 root 3
Oh,
would
2
be your
over
tangent.
4. Sorry.
Yeah, it would be 2 over 4. But 2 over 4 reduces to what? 1/2. So it's exactly the same thing. So if you've got a 30-degree angle, it doesn't matter if you've got a small triangle or a big triangle. The sine of 30 is always 1/2. Never changes depending on the size of the triangle. Okay. Any questions on that? Right. That's why if somebody asked me to figure out, like, what's the cosine of 60 degrees? All I have to do is somehow sketch a 60-degree triangle, or an angle with a 60 in it, and I can sketch any version that I want. I can sketch a big version, a small version. As long as I label the sides correctly, I can figure out the cosine of 60 using any size triangle. All right, so next problem we're going to look at is going to be something like this. They're going to tell you 1 out of 6 of the trig functions. And from there, we're going to figure out all of the other 5. So first, if they want you to figure out all 6 trig functions and they give you one of them, well, they're giving you a fraction. Right? If you're getting a trig function, you're getting a fraction. So that means you're getting 2 out of 3 of the sides automatically. So I'm going to take the information that they give me, use it to label 2 of the sides in a triangle, and then using the Pythagorean theorem, we can figure out the 3rd side. So like if the problem gives me cosine, I know cosine is adjacent over hypotenuse. So I can draw a triangle, label the adjacent, label the hypotenuse, and then use the Pythagorean theorem to get the 3rd side. Okay, so the key is getting that 3rd side. Once you know the 3rd side, then you can figure out anything you want. So if you need to write that, you can, but you probably know most of that. Okay, so once you know all the sides of the triangle, you can determine anything that you need to. Okay, any questions on that idea? let's try this one. So the way I wrote that, let theta be an acute angle. That's important. You're not going to have to worry too much about it right now, but the fact that it's an acute angle tells me which quadrant that this angle is going to be in. Okay? They're not asking for that right now, but eventually they might ask, what quadrant is this angle in? Because you actually have two options. If they didn't say it was an acute angle, it could be in quadrant 1 or 2. Okay? And I'll explain by the end of the week how I know that. It's a little diagram we'll draw. Okay, but it is an acute angle, so it's in quadrant 1. And they just want to know the other trig functions. All right, so let's draw a sketch. Now, when you make your triangle, you don't have to draw it that way. You can draw your triangle any way you want. You can put theta either at the top or the bottom. It doesn't matter. What does matter is that I put the 5 and the 6 in the right spot. So Blake, what's the side that's 5? What is that side?
It would be the opposite.
It's the opposite. So in this picture, where's opposite?
The bottom line.
Bottom. And how about the 6? What side is that one? Yeah, Rachel.
Hypotenuse.
It's the hypotenuse, and that's across from the 90. So the side, Emma, the side that I'm missing here is the what?
Adjacent.
Adjacent, so I need to find that. So you can call it whatever you want. I just call it x. And Robin, how am I going to solve for x?
The a squared plus b squared equals c squared. And
Yep.
you're going to plug in for either a squared or b squared. It doesn't matter.
Sure. Can you set that equation up for me?
5 squared plus x squared equals 6 squared. And then you would do 5 squared is 25 plus x squared equals 36. You would minus the 25 from 36.
All right. And 36 minus 25 is going to give me
11.
11. So we know that the other side is the square root of 11. I would just leave it that way. Unless they tell you to round it, don't worry about rounding it. Okay, so now let's find all the trig functions that we're missing. So they gave me the sine. That one is 5/6. How about the cosine? Yep.
Square root of 11 over 6.
Square root of 11 over 6. And how about my tangent? Yeah,
5 over root 11,
5 over root 11.
which equals 5 root 11 over 11.
Perfect. Any questions on how she fixed that tangent? So we always want to make sure that we, if we end up with a root in the bottom, we have to fix it so we don't have that root.
Why can't you have a root in the bottom?
Why?
Yeah.
Because we don't. The real reason? I think, and this, I could be totally wrong, but before we had nice little devices we could plug numbers in on and hit enter and it gave us answers. This is kind of a hard thing to do by hand. Like if you wanted me to take and divide by an irrational number, but multiplication by an irrational number is easier to do. So if you had to do this by hand, the multiplication by an irrational number is easier than division by an irrational number.
So I can't.
But now that we have calculators, that point is kind of not important. But they still do it. They still do it. But we can look it up after and see if there's a better reason than that. That's the only reason I got for you right now. Spare that. All right, let's see. 3 other trig functions. What's the reciprocal of sine?
Secant.
Cosecant.
Secant is going to be down here.
Cosecant.
Cosecant is up there. And all we're going to do is we're going to flip them. So the first one, that's not bad. Can someone give me the second one, but clean it up, whatever you got to do to give me a nice final answer? Yep.
6 square root of 11 over 11.
Yep. So 6 square root of 11 over 11. And if you could reduce 6 and 11, you would, but you can't. And your cotangent, well, you've got a choice of two things. You could either flip the first answer or the second answer. Which one is less work to flip? I think it's less work. Yeah.
Like the 5 over root 11.
Yeah, why?
Because it would just be root 11 over 5.
And what's nice about that?
You don't have to multiply it by the root.
Right. If you flip the first one, the root goes to the top, you're done. If you flip the second one, it goes to the bottom, then you have more work to do. Okay, any questions on that? Now, if they ask, any one of those 6 pieces of information is enough for me to tell you how big that angle is. That's not what they're asking yet. Okay? But if you told me any of these facts, I could tell you the size of that angle, given that it's acute. Okay? All right, so this one, they're indirectly giving you a trig function. They're not telling you which one they're giving you. It's kind of for us to figure out. Anyone know what the hypotenuse is going to be there? It's going to be a nice answer.
Isn't it 13?
It's 13. What's that called? When you have a right triangle and all the sides come out to integers.
Is it like the Pythagorean triples or something?
Yep, it's a Pythagorean triple, of which there's an infinite amount of those. 3, 4, 5 is one that sometimes people remember. 5, 12, 13 is another one. But if you didn't remember that that was a Pythagorean triple, just use the Pythagorean theorem and find it that way. So, actually, no, let's go like this. Okay, so let's do our 6 trig functions. All right, so we're going to start off with the sine of theta. So what we're kind of doing here, it's kind of weird. We're describing a bunch of things about this angle, but we don't even know how big the angle is. And we're not going to in this problem. Right? It's kind of like if you met someone on the street, and you could describe all sorts of things about them without even knowing their name. You could describe how tall they are, hair color, eye color, what color shirt they're wearing. You don't need to know the person's name to do any of that. Same thing here. We don't know how big this angle is, but we're going to describe a bunch of things about it. So the first thing we're going to describe is the sine. Emily, what's the sine of theta?
5 over 13.
Yep. And this is going to be nice because there's no roots. Kaylee, how about the cosine of theta?
12 over 13.
12 over 13. And Haley, what's the tangent of theta?
5 over 12.
5 over 12. Yep, I agree. And Renee, to get the cosecant, secant, and cotangent, what am I going to do with all those?
Flip them.
Yeah, we're just going to flip them. So we're going to get 13 fifths, 13 twelfths, 12 fifths. As far as the ones we're going to use the most often, sine, cosine, and tangent, we don't use cosecant, secant, and cotangent as much. Also, if you look at your calculator, there's no button for secant, cosecant, and cotangent. So. Any questions on that? All right. All right, so let's use this diagram and try to find the 6 trig functions of 45 degrees. I mean, you can do some of it right now, but really there is something you should find first. Kaya, what should I find first?
The hypotenuse.
Yeah, we can find the hypotenuse. I mean, you can do tangent and cotangent as it is right now. but you can't do anything else. What would be the length of the hypotenuse there? Oh, Tori?
The square root of 2.
Yeah, it's just the square root of 2. For most of these problems, unless they ask for it, you're just going to leave it as a square root. Now, to find the trig functions of an angle, you need to look at everything from the perspective of that angle. Where's the 45 in this problem? Robin? There's 2. So it doesn't matter what perspective you do. Whether you do this one or the other one, all the answers are going to come out the same. And that's because the opposite and adjacent sides are the same. All right, so let's go through our 6 trig functions. And now I don't need to write theta because I'm not working with an unknown angle. I know the angle I'm working with. It's 45. Robin?
Sine would be 1. Opposite over adjacent.
Well, is sine opposite over adjacent?
Or hypotenuse. Hypotenuse.
Yeah, opposite
So
over
it would be 1 over
hypotenuse.
square root of 2, which you can't do. So it would be
2 over 2.
Root 2 over 2.
yeah, that 2.
Sorry.
Thanks, Emma. I wouldn't have gotten it.
Now, the cosine is exactly the same, right? Because opposite and hypotenuse are the same. So that's also root 2 over 2. And then the first one, Robin gave us that one, opposite over adjacent. She said it was 1. So that one's 1. Okay, any questions on that one? Does anyone want me to go through and find secant, cosecant, cotangent? Yeah?
Cosecant or secant?
Yeah, and they're going to be the same. So the secant and cosecant. So your secant is going to be, I would flip the first fraction. And you're done. Just the square root of 2. And same with the second one. So on that one, we got a little confused at first, like which one was sine, opposite over hypotenuse, just trying to remember it. There is a trick which I didn't really mention, but sine is opposite over hypotenuse. Cosine, see, is adjacent over hypotenuse. And then tangent is opposite over adjacent.
I know that. I just always get adjacent and hypotenuse mixed up.
Yeah, so if you can remember that, and just remember which one's which, Sakatoa will help you remember it. I asked this question a couple years back about the trick to remember it, and someone said, oh, Sacagawea. No. Sacagawea is not going to help too much here, but Sakatoa will. So I think she was an explorer, right? She wasn't a math person. So yeah, Sakatoa. There you go. Any question on that? Or you can also try it with the reciprocal functions. So your secant is, what's that? Hypotenuse over opposite. Your cosecant is hypotenuse over adjacent. And your cotangent is adjacent over opposite.
I thought it was the other way. Sine was the cosecant.
Did I? Cosecant would be.
Sine is CSC, and then cosine is SEC.
Thank you.
SEC.
So yeah, secant is hypotenuse over adjacent. Cosecant. Now I'm all messed up.
No, that's right.
Is it right?
It's right, but you just have it in a different order.
Oh, okay. It doesn't even make sense anyway. Don't even bother about it. Just go with Sakatoa, because Choshikao sounds like something I would do. All right. All right. So let's look at this one. Let's say, and even give us labels here. So it says use the diagram below to find the 6 trig functions of 30 and 60 degrees. Well, if they didn't give you any labels, you'd have to be a little clever. So when I see a 30 and a 60, I think, all right, 30 is half of 60. So if this was an equilateral triangle, and equilateral means the sides are all the same. So make them all the same. You want to call them 3, 3, and 3? That's fine. 1, 1, and 1 probably would be even better, because then it'd be smaller numbers. But there's an equilateral triangle, which means all the angles here are what? They're all 60. 60, 60, 60. Now, that doesn't help me to answer the question, because when you're trying to do this, you need a right triangle. But what if I do this? Draw a line straight down to the bottom. Now, let's look at this triangle in red. For that triangle in red, how big is the angle in the lower left? 60. How about the lower right? There's your 90. And that automatically makes the top a 30. So what you did is you just created a 30, 60, 90 right triangle based on an equilateral triangle. Now I know this side is 3. Again, it could have been 1, it could have been 2. We made it 3. How about the bottom side in red? 1.5. Again, not the greatest number. There's 1.5. And now the other leg, I could use the Pythagorean theorem to find it. Right? I probably would have stuck with 2, 2, and 2 maybe, because then when you take half of this side, you don't get a decimal. All right, so let's find the other side. So temporarily, I'll call it x, but we're going to know what that is in a minute. All right, so we get 9 equals 1.5 squared. That's 2.25. Or if you want to think of it as a fractions, 1.5 is 3 over 2. When you square it, you get 9 over 4. And that's 2 and a quarter. Plus x squared. All right, so we're going to get, let's see. What I'm going to do, yeah, you know, we'll just do it as a decimal. What's 9 minus 2 and a quarter?
6 and 3/4.
6.75. Or when we take the square root of it, if you want to get this as a nice answer, you would have to change that to a fraction. So it would be 6 3/4 or 27/4. Any question how I got 27/4? Now take the square root of it. What's going to be nice here is the bottom just comes out to 2. Square root of 27, is that a nice number?
It'd be 3 root 3.
It'd be what?
3 root 3.
Yeah, you can reduce it. You can't take it directly, right? It's not a nice number, but you can write it as the square root of 9 times the square root of 3, or 3 root 3. So there's your exact answer for that side. All right. What was it? 3 root 3 over 2. Right. So now we can find the 6 trig functions of 30 and 60. So what they want you to do in this one is both. Okay? So let me give you guys a couple minutes to try that. So using the triangle in red, I want you to find the 6 trig functions of 30 and then the 6 trig functions of 60. Okay, so 12 different answers. So take a couple minutes, try that, and then we'll get back together and see what you got. All right, so let's start to take a look at it. So the way we chose our numbers for the equilateral, the 3, 3, and 3, kind of resulted in some sides that came out a little messy, especially even this side. You want to think of 1/2 as 3 over 2. We're going to end up with lots of fractions over fractions. So we're going to get a little practice with fractions. All right, so let's start with sine. Sine is opposite over hypotenuse. So let me see. see if I can move some of these down. All right, so I always want to simplify as much as I can, get rid of any roots that are in the bottom. So sine is opposite over the hypotenuse, which is 3 over 1, if you want to think of it that way. And now what do we do when we have to divide two fractions? Do what?
Can't you multiply by those?
Yeah, exactly. So we're going to multiply by 1/3 instead of dividing by 3. So what ends up canceling out there? Yeah.
The 3's
And what do we get for the sine of 30?
1/2.
It's exactly the same answer that we got when I did the sine of 30 back here. Except this was an easier triangle to work with. Didn't end up with fractions over fractions. All right, so sine of 30 is 1/2. How about the cosine of 30? Anybody get that one? Yep, it ends up being √3 over 2 after you reduce it and fix it up. Any questions or anyone want me to go through how to do that one? No? All right, and how about the tangent of 30? 3√3. Yeah. Anyone get anything different, or everyone agree with 3√3? See a couple people looking at me. Let's do that one together and just, I'm not saying whether that's right or wrong, but we'll just go through it. So tangent is opposite over adjacent. So let's see. Opposite is how long? 1.5. Yeah, or 3 over 2. And what's the adjacent? Yep, 3√3 over 2. Well, whenever you're dividing fractions and they have the same denominator, you can just cross those right out. If you want to flip and multiply, same thing's going to happen. So now we've got 3, bless you, over 3√3. Is that okay though? How do I fix that?
Can't you cancel the 3's first and then multiply by the √3?
Yeah, I would just cancel these out. So now you just have 1 over the square root of 3, and then multiply by √3. There you go. And now we just flip them to get the others. So that's 2. 2√3 over 3. And the last one, √3. So those are the 6 answers for 30 degrees. Now, let's look at the 60. Does anybody notice the kind of answers that you got on the right compared to the ones on the left? What ended up happening? Yeah.
Sines and cosines switch.
Yeah. The sines and the cosines are going to switch. Let's just look at one. Well, we'll look at a couple, but then I think you start to see the pattern. So the sine of 60, that's opposite over hypotenuse. That's, let's see, 3√3 over 2 divided by 3. So 3√3 over 2 dividing by 3 is the same as multiplying by 1/3. Your 3's cancel. You get √3 over 2. That's what the cosine was before. Okay, let's do the cosine. Cosine of 60. 3 over 2 over 3. Well, I just did that. That's all the work to do that problem is right there. 3 over 2 over 3 is 1/2. Well, if the sine and the cosine switch, then that means what other two are going to switch? Yeah.
Secant and cosecant.
Yeah, secant and cosecant. So that's going to be 2. That's going to be 3 over 3, and there's only 2 left, and those are going to switch as well. So notice on what happened is these 2 switched places, these 2 switched places, and those 2 are going to switch places. That'll be root 3, and the other one is root 3 over 3. If you pronounce them, it kind of makes sense a little bit why they're switching. Sine switched places with cosine. Secant switched places with cosecant. Tangent, cotangent. So what we call these is cofunctions. All the cofunctions switched places. A cofunction is when you just take a function, put the word co in front of it. Little different than reciprocal, although tangent and cotangent are both. They're reciprocals and cofunctions. But the other ones are not. All right, so let's finish up kind of tying in that idea and what happened there? Why did they switch places? Does that always happen? Like is there certain times when you can just automatically know the other answers if you know something else? And the answer is yeah. And it has to do with complementary angles. What does it mean if 2 angles are complementary?
They equal 90 degrees.
They're each individually equal to 90?
No, together they. So
Together?
If you add up their angles, they equal 90.
Gotcha. So when you add them up, you get 90 degrees. So I'm going to say that the 2 acute angles in a right triangle are always complementary. Why? I don't care what kind of right triangle you draw, the 2 small angles are always complementary. Why? Yeah.
Because the bigger angle is a 90 and a triangle has to equal 90, so it has to be 90.
Yeah, exactly. So I've already used up 90 for the right angle, so the other 2 have to add up to 90. That's why. So when we start to solve triangles, we have to label the sides that we don't know. Usually we use like just English alphabet letters, A, B, C. But we also have to label the angles we don't know. Does anyone know what kind of letters we use usually in trig for angles? Sometimes they use capital letters and lowercase letters, like capital for sides, lowercase for angles, or something like that. What other kind of letters did I mention when we started trig we're going to use a lot of? Yeah? Greek letters, yeah. Now, our book actually does it the way that it was just suggested, capital and lowercase letters. Why do you think I'm going to do it with Greek letters rather than capital and lowercase? Me. Do I like Greek letters? Yeah.
There are a few that look like a C, an uppercase C could look like a lowercase c if it's not big enough.
Yeah, it's kind of hard to tell unless I have a context of a sentence to look at your other letters. Also, if you ask me a question, you say, well, what's B? I'd have to say, what do you mean? You mean lowercase b or uppercase B or side or an angle? So if you ask me what's beta, there's no question. I know you're talking about an angle. And if you ask me what's that one, what is the name of that one? So I kind of gave it away with B. B and beta are opposite. And then A and alpha. So they each start, like if you were to spell them in English, they start with the same letter. A, alpha. B goes across from beta. So when you draw a triangle, you can draw it any way you want. Just make sure C is the hypotenuse, A is across from alpha, and B is across from beta. So flipping it around like that's fine. Just do exactly what I just said. A across from alpha, B across from beta, C is your hypotenuse. So let's look at something in that picture. Let's find the sine of alpha. So the answers here are not going to be numeric. I'm doing this to try to show you something. I want to find the sine of alpha. Yeah. It's A over C. In and of itself, not a very interesting answer. A over C. Now I'm going to find something different. First, I'm going to go with the cofunction of sine. What's the name of that one? Yep. Cosine. And I'm going to pick the angle that is the complement to alpha. So what angle in that triangle did we just say is complementary to alpha? Beta. So I did two things. Cofunction, complement. Let's see what we get for an answer. Cosine is adjacent over hypotenuse. Adjacent is A, hypotenuse is C. And we got exactly the same answer. Okay. There's a lot of them you could do. We'll do one more and see if that happens again. So I'll let someone else pick a trig function other than sine and cosine. How about Jacob? Pick a trig function.
Other than sine and cosine?
Yeah.
Tangent.
Tangent. Right? And pick an angle
Angle.
in that triangle besides one of the acute angles.
Is that beta?
Beta. So we're going to find the tangent of beta. And before I even do it, what else do you think I'm going to find? I'm going to find the cotangent of alpha. And if we do it right, the two things that I just circled are going to come out what? What do you think will happen? Okay, what? Opposites? Well, what happened up here? They came out the same.
Just kidding.
So, based on what happened before, I would tend to think the same thing might happen again. What's the tangent of beta? Emily?
It would be opposite over adjacent, so that is B over, okay.
All right, so opposite over adjacent. So everything was from the perspective of beta. Now we're going to switch our perspective to alpha. Cotangent. We want adjacent over opposite. So from the perspective of alpha, what's adjacent over opposite? Rachel? It's B over A. And this isn't just like a random coincidence. That always happens if you do two things. Cofunctions, complementary angles. And that's called the complementary angle theorem. So very simply, that theorem just says that cofunctions of complementary angles are the same. So you give me two cofunctions. You give me two angles that add up to 90. And the answers to those problems come out exactly the same. So I'll finish up by showing you an example of where you could see something like that pop up on the test. Or midterm. Or one term. So the directions are to simplify that without a calculator. It's the sine of 35 minus the cosine of 55. Now, off the top of my head, I have no idea what the sine of 35 is. I really don't. It's a decimal. It's not a nice angle to work with. And I don't know what the cosine of 55 is either. But there is something else I know that gives me the answer to that problem. Yeah?
35 and 55 are complementary.
30, that's half of it. 35 and 55 are complementary. And what's the other thing that's happening there? You have more than that. They're complementary and, yeah?
The sine, cosine, and cofunction.
And the sine and the cosine are cofunctions. So you have cofunctions of complementary angles. So what do we know about that compared to that? Yeah?
They're going to be the same.
They're the same. I don't know what they are, but I know they're the same, and if I subtract two things that are the same, what do I get? 0. So without really figuring out what either one of those answers comes out to individually, we can figure out the final answer. Now, if the 35 was a 36, it doesn't work. Okay, so it works there. And let's try it here. Tangent of 20 divided by cotangent of 70. What's that going to come out to? Yeah? 1. How come?
Because you're dividing two things that are the same.
Hey, tangent, cotangent, we got cofunctions. 20, 70, we've got complementary angles. We're dividing two things that are the same and we get 1. So subtracting two things that are the same, you get 0. Dividing two things that are the same, you get 1. Could I do this trick with addition? If you add two things that are the same, do you always get the same thing? No. If you add two things that are the same, what do you get?
Double one of them.
You get that thing doubled. So we don't know what that would be. How about multiplication? If you multiply two things that are the same, you get the same thing? No. What do you get?
Double thing squared.
You get that thing squared. And again, we don't know what that would be. So we can do it with subtraction and division, but not really anything else. Let's look at that one. So it looks like it could be a harder problem. It really isn't that much harder. Anyone think they know what the answer is going to be to that one? Yeah. Yeah, it's 5, because what's in the parentheses is 1. And then it's just 2 times 1 plus 3, so 5. Again, what is the cosecant of 15? I have no idea. But I don't need to know it to figure out the answer to the question. Any questions on that? Okay. So now that we've done all this, what we can do tomorrow is, let's say I give you a triangle and you don't have all the information, but you got some of it, like 12 degrees, and that side is 6 feet long. Tell me how big the other angle is, which you could probably do right now. But also tell me how big the other sides are. So tomorrow we'll talk about how to figure that out. Okay, so homework in the book, page 361. 1 through 14, that's all. 16 to 20, just the evens. 21 to 24, that's all. And then I want you to simplify these two. These are like the last two problems we just did on the board. These are not in the book. Okay, so we'll finish 6-5 tomorrow. And then start 7-2 on Friday. No tests this week. Last homework assignment for the term will be on Friday.